All right. How is everybody doing today? Now, what we're going to talk about is something pretty interesting. For today, we're going to combine three things: kinematics, Newton's second law, and work, energy, power. So there's a lot of thing. There's a really a lot of stuff that we're going to cover today. Sit back, enjoy the show. So with every video, here are my general tips that you should try to think about when applying any physics question, especially the part about not rushing, because a lot of times I see a lot of students rushing into it. Oh, I know this answer, and then they realize, hey, that's not really the answer. So don't rush. You should try to use the opportunity to apply these tips in doing the question. All right, and here is the question. There's really quite a lot of words to begin with, and I'm pretty sure that you have seen similar physics question in the very last part of the paper. Some call it a bonus question, some call it an either or question. Either way, it is quite a lot to take in, so take your time to read the question. Submarines. Who likes submarines? I like them. They're pretty cool. Has anyone seen the movie Hunt for Red October? It's quite an old show, but it's a really intense movie, so you should catch it if you have time. So at this point in time, take a break, pause now, work on the question. You can you can rewind the video and read the question, take a blank piece of paper, start working on something. Remember what I said, don't rush, start underlining the keywords, start writing down things. If you are the person who like to do things in your head, I would advise not to. When you write down, your thoughts become clearer. So try doing something different for today. I will begin to talk about the solution soon. Alright, now we have the solution. Okay, so what we're supposed to do for the first question is to determine the time taken to reach the surface of the water. If you're not too sure, this is actually a dynamics question, and you should be drawing a free body diagram. So I want you to take note of a few things. Thrust. Given that there's a thrust force of 9,000, the thrust should be behind the object as it's moving upwards. All right. The thrust is a push force. Okay. If you were to draw the thrust in front of the object, in this case on top of the object, then that thrust becomes a pulling force and is not really very accurately shown in the free body. So take note of that. Weight should be drawn from the middle of the free body. The reason being is that weight acts on the CG, which we will take to be the middle. The last thing is the resistance. Take note that since the object is moving upwards, the resistance being a frictional force must act in the opposite direction to that of the motion. As a result, the resistance is acting downwards. Once you've drawn the three forces and you have a complete free body diagram, apply Newton's second law. So what is Newton's second law? It's the sum of all forces acting on an object equaling to the mass of the object multiplied by its acceleration. Based on that, make sure to take into account sum of all forces. If you apply that into this question, you will get T minus W minus R equals to the resultant force, and that will give you the mass times acceleration, ma, over there. Putting all the numbers, you're going to get A as 3 meters per second square. Now what we want to do is that we need to start drawing a graph, a velocity time graph. Why? Because they said the time, they're asking for the time taken to reach the surface of the water. This as a result, becomes a kinematics question. And as a result, with any kinematics question, you need to draw a graph. And here we have the handwritten graph, uh, quite moderately drawn by a moderate artist, also known as me. You can see here uh, the gradient of, so this graph itself is a straight line, and the gradient of the straight line is 3 meters per second square. And we have the area on the graph being 300 meters. Now you might ask, why is this a straight line? Because we are assuming that all the forces remain the same throughout the whole entire journey from the submarine to the surface. If all the forces remain the same, then the acceleration remains the same. If acceleration remains the same, the gradient is constant, and as a result, you'll get a straight line. Now, why is a straight line starting from the origin? Because the missile was fired vertically upwards from the submarine is taken at rest. Rest means the velocity is 0. Moving on. And here is the kinematics calculation. From the gradient itself, we have v over t equals to 3. Okay, the reason being is that you have two unknown variables. One is v and one is t. V being the velocity of the missile when it reaches the surface of the water. T being that time taken to reach the surface of the water, which we are supposed to find. Combine the two of them, you take v over t, that gives you the gradient. And do we know the gradient? Yes, we do. It's 3. So we have v over t equals to 3. Rearranging the algebra, we have v equals to 3t. Looking at the second part, we also note that the distance is 300 meters, and we know that the area under the graph is equals to the displacement, which is also the same as the distance for this particular case. We can take the area of the triangle which in this case is half base times height. The half base times height will give you the half VT, and that will in turn give you 300 meters. Doing a little bit of algebraic manipulation, and you should get t equals to 14.1 meters per second. We put that as 3SF. Next, average energy loss to the water resistance. Every time when you have friction, and whenever they ask you to calculate the average energy loss to friction, okay, straight away think about work done. That's the key. Think about work done, because that's most of the time that's the only way to calculate the average energy loss to water resistance. There's nothing else that you can use. It's always about work done. Okay, and you might wonder, why do we look at average energy loss? Why is it average? Why can't we just look at energy loss? Because the thing is this: water resistance, as with any type of resistance, will tend to change when the velocity of the object changes. Now, in order to really calculate that, the water resistance will actually change throughout the whole time, and that is not something at your level to calculate. You can't really calculate based on what you know, how to determine the work done by water resistance if the water resistance is continuously changing. You have to use calculus, which is not for the O levels or the IP syllabus. So what we do is that we can do average energy loss. We assume that the water resistance, the force is constant, and it remains constant throughout. So by doing that, it becomes an average. So moving on, we have average energy loss to the water equals to work done by the water resistance as mentioned. Work done formula, what is it? As mentioned over there. Make sure to memorize this formula because it can be a 1-mark question. Put in the numbers and you should get this answer, S3SF. On to the next question. Now we are looking for the kinetic energy of the missile when it reaches the water surface. So write down the formula for kinetic energy. Okay, you've got to remember this formula. We have M, which is 500 kg, but we don't have V. But wait, we do have T. So early on in the question, we have the equation V equals to 3T. Sub T equals to 14.1, you will get the value for V. And then you can put it back to the KE formula and you will get the answer. Great. Alright, now we've come to the last part of the question. Because the last two questions itself are rather related, so I'm going to do the two of them at the same time. So basically we are asked to find the total energy at the end, which is near the surface of the water. If you had if you have just taken the gain in KE plus the energy loss of the water resistance and added them up together, you wouldn't get to the final answer. The reason being is that you have to take into account gain in GPE. Okay, why? Because the missile has gained height, and as a result, gained gravitational potential energy. So you have to put that in as well. How do we calculate that? MGH. Use that formula, put it in. You're going to get 500 times 10. 10 G is 10, and the H itself is 300 meters. You add them up, and you're going to get the following. Which is a rather big number, 2.7 megajoules, and we put that in 3SF. For the last part, we are looking at the minimum power output. Okay, why do I put the word minimum? Because we are assuming that there are no other energy losses. In real life, there will be, so we are assuming that there's no others. So we're just going to put that in. If that's the case, we simply use the formula power equals to energy over time taken. You sub that in, you get 2.7 megajoules divided by 14.1 seconds, and you will get 191 kilowatts. Again in 3SF. So that was fun. I hope you had fun watching, enjoying the video, trying out the question itself. If you're up for it, if you feel good, you try more. Here is another question, a follow-up question to what we worked on earlier. So feel free to try this and have fun trying it. Questions, comments, unclear about something? Feel free to email me at the following address. So if you found that the video helped you and you feel that you've made some progress and you want to make more progress, you want to do more, you want to get the grade that you want for physics, so you can come down for my tuition classes. I have them at Bishan and Clementi. You can contact the center managers for more information, or if you are looking for one-to-one, just email me at the previously mentioned email address and we will follow up from there. In the meantime, I will see you in the next video. Have fun in school, enjoy physics, and goodbye.